Hello and welcome to class time. I'm Denise Bailey.
And I'm Shadeen Cassie, and we are your math teachers for today's CSEC mathematics lesson. Let's begin.
Today we'll be looking at the experimental and theoretical probability. And at the end of the lesson, you should be able to determine experimental and theoretical probabilities of simple events with the use of contingency tables, as well as find the probability of mutually exclusive events. During this lesson, there are some key vocabulary that we'll be exploring, and I'm asking you to pay attention to these so that as we go through, you can tick them off. Probability, experimental probability, theoretical probability, mutually exclusive events, contingency tables, addition rule.
Now, what is probability? Let's recap. We would have had exposure to this before, and we're just going over to move into our objectives.
Awesome.
The probability of an event is a number between 0 and 1 that tells the likelihood of an event occurring.
Okay.
So if we look at the illustration, it shows that there is a probability of 0 for rolling a 14 from a set of dice. And there is a probability of 1 that the sun will rise.
With great certainty.
With great certainty.
Yes, the sun will rise.
And if we toss a coin, there is an even chance. It's a probability of 50%, a half right there.
Yes.
Because it's either the coin will land on a head or a tail.
Yes. Awesome.
The experimental probability. The experimental probability occurs when you actually carry out the experiment or do the event, the action. For example, a coin is tossed 10 times. Yes, we can flip a coin 10 times. And then the results were recorded, and this person got 8 heads and 2 tails. Now, what is the probability of getting a head? The probability of getting a head in this case would be 8 out of 10.
Yes.
Or
4/5.
4/5. And the probability of getting a tail would be 2/10
yes.
or 1/5.
Expressed by this formula.
Yes. So if we want to make a generalized formula, then we can use the probability to be the number of times the event occurs
8
out of the total number of trials.
Okay. And the total number of trials would have been 10.
In this case, it would have been 10.
Okay. And it works for both.
For both.
As you would have done before. Remember, this is just a recap. Okay, so we go to theoretical probability. Theoretical
probability occurs when an ideal situation occurs. So a coin is tossed. What's the ideal situation?
You either get a head or a tail.
Either you get a head or a tail.
Right.
So the probability for getting a head or a tail would be 1 out of 2. Or for getting a head, it would be the same. A half, 1 out of 2.
In theory.
In theory.
Okay.
Now, the generalized formula that can be used to calculate the theoretical probability would be the number of favorable outcomes out of the total number of possible outcomes.
So this is what we know will happen if you toss the favorable outcome.
Right. So you haven't really carried out the experiment as yet.
But so in theory.
Right.
Okay. All right. So mutually exclusive events, though, this is what we'll look at. And what are mutually exclusive events?
Let's see.
Okay. So those events that occur in a single outcome. Either one or the other may occur, but not both at the same time. So let us look at it. When you toss the coin, you can either get the head
or the tail,
but you can't get heads and tail at the same time.
Not at all.
And so that event would be one that we call mutually exclusive events.
Good.
Right? Good. So we can use a Venn diagram to further explain and clarify this whole idea of mutually exclusive events. So we have our universal set, and we have set event A represented by set A. First event represented by set A, represented by set B. Now, when you look at the Venn diagram, what word comes to mind?
I'm thinking about a disjoint set.
And what disjoint set?
They are not overlapping.
Okay.
It's one set and another set. There is separated,
okay.
No intersection.
Good.
Two separate events.
Two separate events. So for those persons who function better with the use of pictures, here is a diagram for you to remember the whole idea of mutually exclusive events. Okay. Now, a fair die is rolled once, and the number at the top that appears at the top is observed. Now, we want to identify the probability that an odd number appears at the top, the probability of an even number appearing at the top, and either a 3 or a 5 appears at the top. Now,
Denise.
yes.
What are the numbers that comes on a dice?
1, 2, 3,
right. So we
4,
are thinking about
5, 6.
those numbers. 1, 2, 3, 4, 5, 6.
Okay.
Good.
So that's a sample space. That's the options that are available.
Those are the chances.
Okay. Now we can represent this information in the Venn diagram, where event A would represent which of the odd or the even?
The odd numbers.
The odd numbers, and set B represents the even numbers. And of course, the sets are both disjointed.
Right.
Good.
Because you cannot be odd and even
At the same time. Not at all. Remember, mutually exclusive events. Awesome. So what's the probability that an odd number appears? What's the probability that an even number appears? And based on the conversation that we had before, it would be the number of possibilities, 3, out of the total, which would be 6.
Yes.
And of course, that would take us to a half.
Definitely.
An odd number appears, that would be a half. An even number appears, that would be still a half.
Right.
But Shadeen, what about either even 3
either
or
a
5?
3 or a 5. So it's the probability that either 3 occur, which would be
1 out
6,
of 6,
right?
1 6, thank you.
Or the probability that a 5 may occur, which would be
Again, 1
out of
1
6.
6, yes. Okay, so we are using the illustration here for us to better appreciate and understand the whole idea of mutually exclusive events. So we looked at mutually exclusive events, and now we want to look at this whole idea of contingency table. I want for you to remember the vocabulary words that we spoke about before. So as we go on, we're asking you in your own words, what are mutually exclusive events? And when we would have completed this section speaking about the contingency tables, you should be able to say in your own words, what are contingency tables and what they are used for, in your own words.
Good. Now, a contingency table provides a way of representing data that can facilitate calculating probability. So in other words, it presents to us information.
Okay.
And we can use this information to calculate probabilities.
Thank you.
The table helps in determining the conditional probabilities easily.
Okay. So
Right.
whichever event we are asked to identify,
You
then
can
we
use
can
the
use
table.
the contingency table to
Right.
help us to clarify. All
Easily.
right? Well, easily.
The table displays sample values in relation to two or more different variables that may be dependent on contingent or
On one another.
Yeah.
Okay. Okay. Now we have spoken about this. Let us see what it looks like. Let us apply this idea.
Right.
Yes, Shadi.
So here we have a table. And let us look at the table. The table is actually giving us some information.
Right.
The information is summarized, so it
Okay.
makes us easy to understand what the table is
Wonderful.
saying.
Wonderful.
Right? And there are different events that are occurring at the same time.
Okay.
So we can highlight that there is a grade 11 class and there is also a grade 12 class.
Yes, yes.
There are students that has cell phone and there are students that do not have cell phone.
Okay.
Can it be that you have a cell phone and you don't have a cell phone at the same time?
Not at all.
Not at
and
all.
so because of that, that is mutually exclusive. So that's a mutually exclusive event.
Right. And
All
can
right.
it be that you are in grade 11 and in grade 12 at the same time?
No.
Not at all.
No. Especially in this case, not at all.
Not
Let's
at
go.
all.
Yes.
So let us take the numbers or the table one at a time. Let us look at the 59. What is the 59 telling us?
It is saying to me that in grade 11, there are 59 students with cell phones.
With cell phone.
Good.
And the 6 is telling us that there are
6 students who do not have cell phone
in grade 11.
in grade 11.
Good. So there is a total number of 65
So therefore,
students
in grade 11, there are 65 students.
in all.
In all.
Both
Okay.
a combination of those with and without.
Okay.
65 students. Grade 12 have
They have 50 students with cellular phone, and there are 3 students with no cellular phone.
in all. In total, there are 53 students in.
grade 12.
So if we know that there are 65 students and 53 students in
Yes.
grade 12, then we know that this sample space is taking up a total of 118
students. Yes.
Good.
Yes.
So there are a total of 109 students that has cell phone,
yes.
and there are a total of 9 students with
Without
no
cell
cell phone. All right,
Okay.
good.
And so it is important, what I'm hearing you say though, Shadid, is that when you get the contingency table, you have to pay attention
To all.
to all the information
Right.
and ensure that you truly understand. Yes.
There are some questions, Denise, that we're going to be discussing. What is the probability that a student from grade 11 has a cell phone?
Okay. And
What is the probability that a student who does not have a cell phone is from grade 11?
okay.
Which two events are mutually exclusive?
Okay, so we can explore that a little
Right.
further now. Yes. So the first question you asked is the probability that a student from grade 11 has a cell phone. Now, I have to be reminded of the formula as we spoke before. We have to be reminded of the formula. And so we have to identify the number of grade 11 students that has a cell phone, which would be 59 of them with cell phone. And we have to understand and know the total number of students that are in grade 11.
Right.
And so, based on what we have here, the probability of a grade 11 student having a cell phone is 59 out of 65.
Denise, before you go any further,
Please.
why is it that we are looking at 65 students instead of looking at 118 students, seeing that we are referring to total? Remember, it clearly identifies that we are looking at grade 11.
That is the parameter that we're working in.
Right.
So
Or
the 118 represents everybody, both grade 11 and grade 12. But
Good.
they are specific to grade 11. Okay. Okay. The second question was, what is the probability that a student who does not have a cell phone is from grade 11? So you don't have a cell phone.
And you are in grade 11.
And you are in grade 11.
Right. So, don't have a cell phone, and in grade 11, we're looking at 6.
Yes.
Right?
No cell phone, grade 11, 6. Awesome.
And the total number of grade 11 students, the total sample space
would be
65. So let's move into.
Okay. So that information is represented here, but hold on. The total number of students who do not have a cell phone and the total number of students with no cell phone. Oh, wow. Interpretation of the contingency table. The total number of students who do not have cell phone is 9.
Right.
Is actually
so
9.
We are not just referring to the grade 11 class
alone.
Right?
Yes.
We are referring to the total number of students with no cell phone. Correct.
Okay. And so, ladies and gentlemen, we have to remember that when we are working with the contingency table, we have to pay attention to the information. Pay attention to what is asked.
And what is given.
Thank you very much. Yes, so of course we see that we have 6/9 representing the probability of students from grade 11 who don't have a cell phone. Okay, and the 6/9 when simplified is 2/3. Okay.
Let's examine the contingency table. It's the same question, but then part C. Which events are mutually exclusive?
So you're saying, remembering that mutually exclusive events, they cannot happen at the same time.
No.
So as we had discussed before,
earlier, you cannot be in grade 11 and grade 12 at the same time.
So that's mutually exclusive.
Right.
So that's one pair of events. And you cannot have a cell phone
and
not have a cell phone at the same time. So there are 2 pairs of mutually exclusive events
that are highlighted in this contingency table.
Awesome.
Or say summarized in this contingency table.
Okay, we can understand that.
Now, when one understands what the contingency table is all about and the information that is given, then we are able to pull it apart and put it back together.
Okay.
Now, in this case, here we are given a question that some of the information are missing. So it means that based on our understanding of what is given
and how the contingency table actually works,
we should be able to fill in the missing spaces.
Should,
right.
Okay.
So, they are referring to sporting preference. The table shows a random sample of 100 adults and the sporting activity they prefer. Let's complete the table.
Okay.
Now, Denise, I'm looking at 45 and I'm looking at 55.
You know,
and let me tell you something, Denise, before you go into it, there is no one way of completing this table.
And no one order or place to begin.
Right.
Just reason it out. Yes.
So the 45 and the 55, they just jump out at me because probably they are the largest number on the table.
Okay.
So I see that those 2 numbers falls under the total.
Yes.
And I remember upon reading the information given that we were told that there are 100
adults.
So I really don't need to do any calculation to fit in.
No, not necessarily.
100.
That is
all right.
given. Yes.
And because we are females, not to say that we are gender biased, but female, I see 18 for football, I see 16 cricketers, and we need to find out the number of basketball players.
And we have the total.
And there is a total.
Yes.
So basic arithmetic, 16 plus 18 will give us, and then we take that total from 45,
which would give us 11.
Good.
Yes.
And if we know, might as well we just continue completing.
Because more information is now being given. So the more information we have, the more we are able to complete.
And the easier to.
Thank you.
Right. So it's 11 plus 14 that will give us
a total of 25. So 25 persons. And for basketball,
we see that there's a total number of 41 cricketers. And we have 16 already being female.
Okay.
So the rest would be Males.
Basic subtraction.
Basic
Good.
subtraction.
Yes.
All right. And then we should get a total of 100 over there.
That's right. And a total of 55 here.
And a total of 55 there.
Yes.
So either way, we can just go ahead and complete our table. Right.
Awesome.
So it would be
awesome.
Exactly.
And so, boys and girls, sorry, ladies and gentlemen, this is how we can use the contingency table to help us to work through this whole idea of probability. Before we get to the probability itself, we have to understand the contingency table. We have to know how to use the contingency table and input information.
Denise, before you go any further though, we have been talking about mutually exclusive events.
That's right.
We also said that the contingency table can present information about
yes.
2 or more events, right?
Yes.
Can you identify some sets of
Mutually exclusive? Okay.
Right. So you can't be a male and female at this.
That's...
You can't be...
Let us go to the not the gender. Let us go to the sporting activities.
Right.
I feel safe there. So for the persons who responded, it's either football or cricket or basketball. And
right.
so that for me is a set that shows the mutually exclusive events, but not just of 2, but 3 mutually Oh, so that means, Shadeen, you can have more than 2 mutually exclusive events.
Right, which is also what our definition had stated before.
Awesome. So now, ladies and gentlemen, you should be able to, for yourself, write about the contingency table in your own words.
And we are going to challenge them too to just create some simple probability questions and answer them from the table that's produced right there.
That's provided. Okay. Now, next, we will be exploring this whole idea of the addition rule and the contingency table. We have looked at
mutually exclusive
events. And so, what is this thing called addition rule? Okay, so let's look at this. Now, we have some solids, green, and we have two colored sets solids. We have green and we have blue.
But let's talk a little bit about those solids. So we are seeing cubes.
Yes, the cubes, cylinders and the spheres.
Right.
And they are also cubes, cylinders and spheres in the...
Could we say that there are a set of mutually exclusive sets that are on the board right there? Yes, because there are specifically stated green and there are specifically stated blue solids that are
and
there.
so that is that the color could be green or blue, a pair of mutually...
Right.
But what are mutually exclusive events? But what about the solids themselves?
Right. So all this can be presented in a table, right? Because the contingency table based on the question that you're asking, and there is no way you can be a cube and a cylinder at the same time.
Or
right?
a sphere and a cylinder, or any of the combination.
It goes back to more than 1, more than 2 events occurring at the same time.
Okay.
Right.
So what if we were to now place all these solids in this beautiful bag and summarize the information on the contingency table? Simplify, don't it?
It's much easier. I can pick out any information I want. If I want to find out how many green cuboids there were, it's telling me 6. If I want to find out the total number of cuboids that is in the bag, then I know that there is 10. And if I want to find out the number of cylinders, the total number of cylinders, whether it be green or blue, I know that it is 5. If I want to identify the number of spheres that are there, the ones that are green, I can tell you that it's 5 right there. And if I want to find out the total number of solids that's identified, it's 22.
Wonderful. And so this is how we can add to use the contingency table, but remember, we're looking at the addition rule in a bit. We're going to take a quick break, but we'll be right back with more CSEC mathematics.
Welcome back to class time. Let's pick up where we left off.
Now, where we left off, Shadeen, was this whole exploration with the solids that we have. And so we're going through this in the solids that we have in order for us to move forward. Good? So we said that we had two separate colored solids placed in a bag. The solids were spheres and cylinders and cuboids. We placed them in the bag and we have put the information on a contingency table for clarity. And we are now going to use the contingency table to help us to explore and understand this whole idea of addition rule. Right?
As it relates to the content.
This specific information.
Right.
Okay, so we're all caught up.
But Denise, before you go any further, I think it would be appropriate if you just spend some time to just analyze the information that's in the table.
Okay. From the conversation, we had mutually exclusive events.
Right.
We had cylinders and we had cubes, 10 cuboids. We had spheres, 7 spheres, and the cylinders, there were 5. We had a total of 22 solids that are in the bag. Placed in the bag. We know that there are a total of 9 blue solids and a total of 13 green solids. And we also know
that if we want to identify individual solids per color, we could go inside the table.
So that is just a quick review of the information that we have on this contingency table. Awesome. So now we will use the contingency table to select mutually exclusive events. First, which events are mutually exclusive? And we went through those. Take a couple seconds. Can you say which events are mutually exclusive? I really hope they can, because we actually did it
went through that. We gave the answers several times. All right. So the green solids and the blue solids are mutually exclusive events. And if we talk about the solids individually, the cylinders, the cubes, and the spheres, they are 3 sets of mutually exclusive.
Okay. I hope you had that. I hope you had written that down as your answer. Good. So let us look at using the contingency table now. What is the probability of selecting a cube or a sphere?
So let's examine our table carefully, right? So we will find the total number
Cube.
of cubes.
Yes.
Right, because it didn't say a green or a blue cube. And then that's 10.
Okay.
So what is the probability of selecting the number of cubes? It would be 10.
Cube. Okay. Yes.
Out of the total, which would be what? 20.
10 out of 22.
Right.
Okay.
And the probability of getting a sphere.
That the probability of the sphere total, because they didn't ask us specific to color, right?
No.
So we'd look at the total, and it would be 7 out of
The total.
22.
Right.
All right. But it said a cube or.
So
And what
need
we
to
would
do-
have just done is to identify each event.
Right. So we need to do
Okay.
some form of combination right there, find some way
Okay.
to put this information
But
together.
I wonder if you guys at home are able to come up with an idea of how it is you could find the probability of selecting either or. Okay, let us see what happens. So, of course, we have our contingency table, and as we had discussed before, we would select event A, in our case, would be selecting the cube.
Right.
And the probability of selecting the cube, that would be?
10 out of 22.
Okay. And event B, which would be, which of the shapes? The solid
The sphere.
The sphere, okay, that's event B. That would
7
be?
out of 22. Right.
Okay. So it is important for us, even as we're finding either or, for us to first identify the specific events, the probability of finding the specific events. Okay. So the probability of selecting a cube or a sphere now, what do you think we would need to do? Shadeen said something earlier. I heard her say something about some combination of sorts, right? That's
Right.
what I heard.
So based on what the question is asking, it didn't just ask us to identify the probability of one or the other, but it's a combination basically.
Okay, okay. Event A, the probability of finding event A, added to the probability of finding event B. And if we add the probability of finding event A to probability of finding event B, then we have a sum. And that sum would be probability of finding event A added to the probability of finding event B.
Good.
And it is clarified further for us because we have actually done this, you know. So what would be the probability, what would be probability of A added to probability of B?
All right, so it is requiring of us to add 10 out of 22, and we're going to add that to 7 out of 22, which will basic addition of fractions that will be carried out there. And if you can see, we're adding fractions that have the same denominator.
Like denominators.
Like denominators,
yes.
right? So we can just move ahead into adding the numerator, and that will give us a total of 17 out of 22.
Awesome. Now, addition rule. Remember, as a part of the vocabulary words, we had this whole idea of addition rule, right? We have not specified it as yet, but are you seeing a pattern? What are we talking about when we say addition rule? And we have here a sum which says the probability of A added to the probability of B. I wonder, could this be the addition rule? The addition rule of probability is exactly that, where we find the probability of event A added to the probability of event B. And this is what the probability rule states. What does it say, Shadeen?
The addition rule states that the probability of two mutually exclusive events is the sum of the probability that either will happen.
Two mutually exclusive events.
two events
Yes.
occurring independently
of each other.
Right.
Okay. So for us here, it's for mutually exclusive events. And this is the probability rule. Do you think you are able to write in your own words the addition rule? Explain it, because this is quite easy for us to remember, not true?
Quite easy
yeah,
for
man,
us.
we can remember that. Probability of A plus the probability of B, that's the addition rule. What does it mean? Write it in your own words. Because remember, we had the vocabulary words at the beginning of our lesson. Okay.
And it is for mutually exclusive
Thank you.
events.
When we're talking about the probability of A added to the probability of B and using this as the addition rule, it is for finding the probability of mutually exclusive events. Now, help me. Take me through this one, please.
All right, so we are going to go through a sample question, and we are applying the addition rule, the probability, as it relates to probability. And the question is, a bag contains 7 red and 9 green, as well as 14 blue and 10 marbles. 10 orange marbles.
Yes.
What is the probability of selecting a blue or a green marble?
Okay.
As well as, what is the probability of selecting a red or orange marble?
And Shadeen, can I say to you that if we can find those probabilities, we could also find the probability of selecting a green or orange
red or blue.
Wonderful.
Any two.
Any two.
Right.
Or I wonder if 3.
It works with 3 as well.
Okay.
Right.
So let's look at it.
So the first question was asking, what is the probability of picking a blue or a green marble?
Okay.
So what's the probability of taking a blue marble?
You want to take us through it on the
whiteboard. So let's go back to the
question itself.
question.
Yes.
So we are just going to do a summary of the information that's given. So we know that we have 7
red, 9 green,
9
14
green,
blue, and 10 orange. There is a total of, because that's where I'm going. What would be the total? How many marbles are in the bag?
All right, so once we're looking at probability, it is important for us to consider the total.
Okay, good.
All right, so what would be the total number of marbles?
That is what, 16 plus 14 plus 10.
It would be 16 plus 14.
That's 30.
Plus 10.
40.
So in all, we're working with 40 marbles.
Okay. So we now have the total. Yes.
No, the first question wants us to find the probability that we're selecting a blue or a green marble.
Yes.
Now, can we have a marble that's blue or green and green at the same time?
Not in this.
Not in this case. So what kind of event are we dealing with?
2 mutually exclusive events.
Right. No. For blue, probability of getting a blue marble. How many blue marbles do we have?
There are 14 blue marbles.
14 blue marbles. And what's the total number?
Out of a total of 40 marbles.
Good.
So that is the probability for blue.
For blue marbles.
Okay, awesome.
Yes. How many green marbles are we working with?
9 green marbles.
So the probability, and if you notice, I'm using the P to represent probability, right?
Yes,
That's a given. And we have 9 green, and the total number of marbles,
of course, remains the same. It's 40.
40. Good. Now the probability for the 2 mutually exclusive events, I'm representing the formula here, would be the probability of blue plus the probability of green, which will give us
14 out of 40 added to 9 out of 40. And this is simple addition because, again, we are adding fractions with like denominators.
Right. So we will get a total of
14 and
23.
23. A represents the event and B represents the other mutually exclusive event. If you should look on what is identified here,
right, we're not using A or B, but we are using B for blue marble.
That is the event. Blue, it's the event. So you could write out the blue. So the probability of blue added to the probability of green. So in the addition rule, we have probability of A added to probability of B, understanding that A is an event and B is another event.
And before you go to your solution on the board,
I'm
just going to work part B as well.
Please, thank you.
So I'm going to be erasing this.
Not a problem.
Right? Please make note if you didn't have it correct.
Yes, yes. So while she's erasing the board, could you go ahead and find the probability of selecting either a red or an orange marble?
No, this time we are working with red or orange marbles. So how many red marbles are there?
7 red marbles.
But before we go into the number, let's represent our formula, right?
Yes.
So it would be probability of
event
with the red marbles.
Okay, added to
the probability of the event with the
orange marble.
Orange marbles.
Okay.
And we know that there are
7
red. And the total remains
40.
What? 40.
Yes.
And there are
orange 10.
10 orange,
yes.
And the total remains 40. So the probability of red
selecting red or orange,
right, would be
17 out of 40. So that's the probability. And what Shadeen has taken you through is the probability rule and how to apply the probability rule for mutually exclusive events. And what I want us to remember, that even though the rule speaks to 2 events, as we saw earlier, you can have any number of events. What you are to ensure is that they understand what is expected of them.
And just for challenge, you could just stretch yourself to say a probability of selecting a red or a green or blue and see a 3. Right.
Okay, wonderful. We're going to our final break. We'll wrap things up when we return. Soon come.
Welcome back.
Now, before the break, we were working with the probability or finding the probability of selecting either a blue or a green marble, and we used the probability rule to help us to be able to make identify the probability. Shadeen worked the solution on the board, but we also have both expressed here for us. And you would have seen that based on the calculations that you had done on the whiteboard, that of course we are. Yes, what's happening
I'm
now?
just going to highlight because we worked in fractions, but here we are presenting percentages.
Is there a challenge though, or is there an issue with using the percentages here?
Probability can be represented as fraction, decimal, or as percentage.
Awesome.
So it depends on whichever you are comfortable or specifically
to
what the question requires.
For. Okay,
yes.
good. So please bear that in mind. Refresh yourselves. Probability can be represented using the
fraction, decimal, percentages.
Okay.
Or but your response depends specifically on what the question requires.
Okay, good. So let us continue with the application of the probability rule. Now this question is just a little different. It says we have an event 1 and an event 2, which are two mutually exclusive events, and they have the probability of event 1 being a half and event 2 being 2/5. Now, we have the question, well, two questions. What is the probability of selecting either event 1 or event 2? And what is the probability of selecting neither of the two? So we are still doing probability, but it is in a different format.
Right.
Do you think you would be able to tell what's your first step? What would be your first step?
Well, my first step would be to identify the probability of event 1
and event 2.
Okay. Right. This is what CSEC will require of us, like questions like these. So this is really taking it up to what CSEC requires.
Yes, application.
So, event 1 has a probability
of a half.
Yes. And event 2,
2/5.
2/5. And we need to find the probability of either event 1 or event 2 occurring. So the generalized approach would be the probability of event 1 added to the probability of event 2.
Okay. Event 1 is
a half,
then.
And event 2 is. Are you noticing anything different?
Yes, all along when we were using the addition rule, we were adding fractions with like denominators. But when we get here, we're seeing that a half and 2/5, they are unlike fractions. So I'm going back to primary school now.
It's okay.
I have to use that information.
Right.
Yes. So the information that I'm thinking of, Shadeen, is the whole idea of equivalent fractions.
Equivalent fraction.
How would you use the idea of equivalent fractions to solve this problem right here?
Now, once we are talking about equivalent fraction, then our next step would be to identify a common denominator.
Yes.
And in this case, the lowest common multiple would be
the lowest common denominator.
Right.
All right.
And we have the denominators being 2 and 5.
Okay.
So our lowest common denominator would be 10.
Okay.
Right? Now, if we were to write half a half as an equivalent fraction with a denominator of 10, what would that be?
The numerator for me would be 5 because 5/10 is equivalent to 1/2.
Right, good.
Okay.
And if we are to write 2/5 with a denominator of 10,
Yes.
and
The
what?
numerator for me would be 4.
4.
So 4/5 would be equivalent. Sorry. 2/5 would be equivalent to 4/10.
Right.
Okay. Okay, so now we come
Now that we have a common denominator,
Yes.
we can just go ahead and add the numerator.
9/10.
9/10.
Therefore, so would we be complete? Are we finished then?
We are finished with part A of the question.
So therefore, the probability of either event 1 or event 2 occurring is 9/10.
Right.
Using the probability rule, which is probability of A added to event A added to the probability of event B. In this case, however, the probabilities were given to us and we had fractions with unlike denominators, and so we had to find the equivalent fraction. Okay, so what about the probability of neither?
All right. So since we know that the probability of either event 1 or event 2 occurring would be 9/10, then neither is a given, right?
Yes.
We would
yes.
have completed most of the work already. So it would be the total probability, which would be
10 out of 10.
10 out of 10, a whole, right?
Yes.
And then we are going to be doing the flip side to it.
Okay.
Right.
Okay. So if I have 9/10, what do I add to 9/10 to make it one whole? So 9/10 added to 1/10 will give us 10/10 or one whole. Therefore, the probability of neither event 1 or event 2 occurring is actually 1/10.
1/10.
Awesome. Okay, we can live with that. And of course, this is what you had on the solution set expressed earlier. Now,
just go back so persons can examine.
so what we have here is a question that we're going to ask you to begin to work for yourself. So it says that you have a 10th grade class and they have chosen their electives. 50% of the students did literature only. They will do literature only. 17% of the students will do geography only. And 13% of the students will do physics only. The remainder of the students will do agricultural science only. The questions, we ask that you take these questions. If a student is chosen at random, calculate the probability that he or she does literature, geography, or physics. Now, when we say that, I'm looking at 3 mutually exclusive events. And what is the probability that he or she does neither literature, geography, and physics? And so what would your first moves be? Remember the example that we had before that you worked for us. We can put the information on a table. This is not a contingency table, no. It's just a little table to clarify what it is we desire. The information that we have, sorry. So here, what is the probability that he or she doesn't choose any of the 3? First, we have to identify the total.
The question mark. Address the question mark.
Address the question
so
mark.
So we were given the total because
as a percentage. Good. So if we had 50% added to 17%, added to 13%. Now this is for you to do on your own. What we're doing is walking you through. So after you would have identified the percentage, remember, 50 added to 17 added to 13 added to what gives you 100, right? Because it's percentages we're doing. Okay, and of course, what is the probability that he or she does neither literature, geography, or physics? And today, we would have learned about the use of the contingency table to predict the probabilities of simple events, as well as explore the addition rule for the probability of mutually exclusive events. I hope you learned something new today. That's all the time we have for this lesson. Thank you so much for joining us today. Until next time, keep safe.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.